All right, so for the last topic in the entire course, we're going to be talking about polar form again. So when we're talking about polar forms of equations, we have to talk about some equation that takes r and theta and generates, points of a curve. So if we're going to do that, we're going to have our little setup here. We're going to let this be the focus of our conic section. This is going to be a point on the curve. And what's cool about this idea of conic sections in polar form, we can define them almost with only one equation. And the only thing that's going to determine whether it's a ellipse or parabola or a hyperbola is going to be a value of a single number. Rather than looking at an equation and going, oh, look, they both have x squared terms, an x squared term and a y squared term, and there's a plus in between them. Therefore, it's an ellipse. That requires three pieces of information. A polar form is only going to require one to be able to determine which graph it is. All right, so F is a focus, P is a point on the curve itself, and this point D is on the line x equals D, which is our directrix. And of course, D is perpendicular distance away from point P. So this curve, the way we have it set up, is going to basically be a left-right ellipse, or a left branch of a parabola, or the right side of a parabola, or it's going to be a hyperbola that opens up left and right. So if we wanted to come up with the ones that go up and down, we would just need to move the directrix to be y equals d. And that comes up with a whole nother equation, but we'll talk about that very generally after we get this one set up. So to make this a polar form, we're going to need a theta. And automatically, because FP goes through the origin and theta is pulling the line segment FP away from the positive x-axis, then in polar language, this is the radius of the rotation. Okay, so we already know part of our polar equation, and we already have a theta in here. The only thing is we need to determine some other ideas. All right, so our picture is perfectly fine right now. Now we just got to talk about the math side. So we're going to define this idea of eccentricity. This is going to be the one value that is going to determine if we're looking at an ellipse, a parabola, or a hyperbola. And it's set up as the point on the graph, distance to the focus, divided by the point on the graph's distance to the directrix. And we're going to call this thing eccentricity. We're calling it E, but don't get confused between the natural number E and eccentricity E. So if we're working with conic sections in polar form, this E has nothing to do with the natural number. All right, so if we kind of set this equation to be, solved for one side, we're going to get PF equals E times the distance of PD. I debated using vector language here, but I think we understand what we're talking about here. Now PF we already know. PF is R, so I can replace this with R. And then I get E times PD. PD is this length. Here, if we, extend it a little bit further, the orange and the red is the entire length of D, because we're going from the x-axis all the way to the line x equals D. So that length is D. We'll put a little D down here. So if that length is D, then to find the orange length, we just need to get rid of the side. So I need to know the length of that side of the triangle. And that's easy enough to do. We should know what that is pretty quickly. If I call that x, this becomes cosine of theta is equal to x over r, and therefore this side becomes known as r cosine theta. So this length from here to here is r cosine theta. So that means the orange line up here, let's switch to orange, is going to be the d length minus that little piece down there, r cosine of theta. Okay, so we can substitute that into our formula, and this becomes d minus r cosine of theta. Cool. Now, for conic section, or I'm sorry, polar form equations, we need to solve for r. So we're gonna, distribute the e. Oops. ed minus er cosine of theta. We're going to get the r's on the same side of the equation. I'm going to factor out an r. And then divide both sides. So we get this equation for all conic sections that are facing left-right and d being positive. Now, if d is negative, the only thing that changes is that plus. If d is a negative number, then the plus sign turns to minus. That's all that happens. So ed over 1 minus e cosine theta puts the directrix on the other side of the y-axis. So it's a minor change. All right, now let's talk about our eccentricity up here. So PD over PF. We know what it's equal to for parabolas already because we defined a parabola. I'm going to sketch this and then erase it. We defined a parabola to be all the points on a curve that is equidistant from the focus to this point P and a directrix on the other side. So we already have this equation for a parabola all set up. Now notice this is different than my picture above. My directrix here is on the left and my parabola is facing to the right. So if I flipped it around, it would be facing the other way. So this one up here, the parabola would be facing the opposite direction, but that's neither here nor there. Because these things are equal to each other, this would be the point D over here. PD is equal to PF, that means the eccentricity would have to equal 1. So if we're talking about a parabola, then E is equal to 1. All right. If I showed you that, I'll have another video showing you how the conic sections are generated using this thing, and it kind of gives you a better understanding of these lengths, PD and PF. It's hard to draw here, so it'll be right after this part of the video. An ellipse, the eccentricity is between 0 and 1. And for a hyperbola, the eccentricity is bigger than 1. So if you have an eccentricity that's equal to 1, we're talking about a parabola. If we have an ellipse that's between 0 and 1, we're talking about an ellipse. If we have a hyperbola, then the eccentricity is bigger than 1. All right, so they all are this equation where the eccentricity determines what graph we are talking about and the directrix determines its shape. Polar form of some conic sections. And the nice thing about the polar form about conic sections is to change the conic, all you have to do is change the eccentricity. So here I have the eccentricity as being capital E because in the program little e is, the exponential function. D being the directrix, this hot pink line over here. And K is actually my theta that I'm going to rotate it at. So I've set it here at 2.56 theta, and that's this opening right here. So from here to here is 2.56 radians. And this is the function's radius that r equals, in this case, ed over 1 plus e cosine theta. So that's the length of this radius here, according to theta equaling 2.56, directrix equal to 3, and e equal to 0.6. So when I put this thing into motion, I have P tracing some points to give it its general shape. So let's bring it back to 0. And you start seeing that the rotation, of course, is going backwards because we're going towards 0 radians. And then if I go forward again, it graphs out the full rotation. So here would be pi radian rotation. And then as we wrap it back around, we get back to 2 pi. So when the eccentricity is 0.6, then the graph of this thing kind of looks like this. And you'll notice when we were here at 2. Let's see if I can get it back to the 2.56. There it is. That PF, the distance between the point on the graph and the focus, is smaller than PD. So when you do the PF over PD, since it's a small number over a big number, you're going to get a number between 0 and 1, and that's why E is 0.6. All right. So let's change E and see what we can get out of it. So if we change E to 1, and you can kind of get the sense that PF and PD are equal to each other. So therefore, eccentricity is equal to 1. All right, so when I start rotating this out, it starts going really crazy after it gets far away. So I had to go negative with this one. And rotate the other way, what happens is it forms a parabola. And then if we change where D is, it changes the shape of our parabola. So if I put D way over there and start drawing, it makes a fatter parabola. So the further D is away from the focus, the fatter the parabola gets, even though the eccentricity is not changing. So the eccentricity and the directrix give you this picture shape. All right, so let's go a little bit bigger than 1. Let's shake this up a little bit. If we go bigger than 1, you can kind of see that PF is getting bigger than PD now. Let's go to 1.5. And then probably zoom out a little bit. This picture is a little different. So when I start rotating my angle, it goes off the screen rather quickly, but it goes on both sides of it. So this is negative 2.84, which would be in the second quadrant, but then the radius must be negative to shoot it over there into the first quadrant. Remember those nice things called polar functions? And then if I rotate it the other way, it comes back over here. And again, you can see PF is bigger than PD, and therefore the eccentricity is larger. And we get a graph that looks like this. Now notice the further branch of this hyperbola, the dots are not as consistent, and it's because we're further away and the angle changing the radius much longer also. So if I would just put the picture in there, we get this. So again, if I start changing D, it changes the general shape of the picture. And if I change the eccentricity to be bigger, it becomes fatter that way also. And then get it closer to 1, and it becomes kind of thinner around those foci. So the other foci is over here someplace. It's just kind of hidden. So that's the polar form of conic sections. This one, of course, is only going left and right. I'd have to create a whole different one to force these things to go up and down. Some other definitions of eccentricity that'll help us actually physically graph these polar equations a little bit easier will be one of them coming from the idea that eccentricity is equal to C over A, where C is the distance from the center of the conic section to the foci, and A is the distance from the center of the conic section to the vertice. Now, of course, this only works for ellipses and hyperbolas because the eccentricity of a parabola is just 1, so we really don't need to know all of this fancy stuff. All right, so here we have a polar equation, r equals 4 over 3 plus cosine of theta, and I want to find out which conic we're talking about. Are we looking at a parabola, hyperbola, or an ellipse? And then I want to use as much information as I can gain out of this to graph it. The graphing part is not as easy as it seems, and there's different viewpoints you can take on it. So the general form of a conic is R equals ED over 1 plus E cosine of theta. So we're going to try to make this thing look a lot more like this guy down here. Now to start that off, the easiest one to change is this 3. Because all we want to do is change that into a 1. So I'm going to take my original graph, or my original equation, and write it as R equals fraction, change that 3 into 1 by dividing by 3. Now if I divide him by 3, I have to divide everybody else by 3. So the 4 by 3 and the cosine by 3. But I'm going to write it as 1/3 cosine of theta. Okay, so now it looks a lot more like what's above after I simplify. So I get 4/3 over 1 plus 1/3 cosine theta. So this is actually the easy part. Because right off the bat, I know what E is equal to, because E is the coefficient of cosine, and the coefficient of cosine is 1/3. So I know for sure that the eccentricity of this graph is 1/3. The other thing I know about it is this is an ellipse, because the eccentricity is between 0 and 1. 1/3 being a number between 0 and 1. So we know what E is equal to. We also know what D is equal to because ED, in this case, the top number in that position, is 4/3. So ED is 4/3. Well, if E is 1/3, then D is definitely 4. So that gives me where my directrix is. It's at x equals 4. I know this one is facing up and down for the directrix because it's cosine in the bottom. The other option is sine, and then the directrix would be going left and right. So this is a vertical directrix. And I can get an idea that my ellipse, because the directrix is vertical, is going to be the type that is drawn with a longer major axis going left and right. So my major axis is going perpendicular to the directrix. All right, so given all that information is nice, but now I want to come up with graphing this thing. And to graph it, we have to get it back to x squared over a squared plus y squared over b squared is equal to 1. Because that's really the only way, nicest way to graph a conic section. It's a little bit harder. I mean, you could do a table of values and graph it directly from up here, but that's really not the best way to do it. All right, so let's see if we can find what a and b are equal to. So the other two formulas that we're working with for eccentricity is E is equal to C over A. Now when using this formula, we have to be a little bit cautious. When we talk about this, we're talking about C and A coming from this formula up here. But you also have to remember that when we do the graph polar style, that we're putting a focus at the origin. So more than likely what we're going to be dealing with is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. I know my focus is on the x-axis, so right off the bat this k is equal to 0 because we're not going up and down. We're not translating it. We're shifting it left or right depending on a few things. So when we talk about A here, let's say our center point is here, center. Then this distance from the center of our ellipse to the foci, this is going to be C. And let's go purple. This distance from the center to wherever the heck the vertice is, i.e. vertice, this distance will be A. So the first thing we have to find is the center of this thing. So I know what H and K is, well in this case, what H is. And then we can determine what A is. Then we can determine what C is. And then finally we can figure out what the equation of it is by finding B. All right, so first things first, let's go back to our equation. R equals 4 over 3 plus cosine of theta. And if we're looking for a vertice, this position here, theta for that one is equal to 0 because it would just be lying straight out. So if I let theta is equal to 0, that's going to generate r is equal to 1 because cosine of 0 is 1, 1 plus 3 is 4, and 4 over 4 is 1. And then if we go for the other easy one, which is pointing in the other direction, that would be theta is equal to pi. And if we plug in pi, cosine of pi is negative 1. So we're going to get 4 over 2, better known as 2. So that gives us a line segment or a coordinate system where this is a foci. When theta is equal to 0, we're getting a point on the graph over here. This is my first vertice. And when theta is equal to pi over here, remember, when we're talking about pi, we're looking in this direction as being positive. So we're going 2 units out on there, and there's v2. So this one is at x equals 1, and this one is at x equals negative 2. Oops, didn't leave myself enough room. X equals negative 2, and x equals 1. So if these are my vertices of my ellipse, then that is the major axis. So the major axis is also known as 2 times a. So here I have 2 times a is equal to 3, and that gives me right away that a is equal to 3 halves. All right, that's kind of cool. A little bit of a messy process, but it'll still work. Now I can take this a equals 3 halves and the formula E equals C over A and find out what C is equal to. So this implies that 1/3 is equal to C over 3 halves, which makes C equal to a half. All right, so now I have 2 of my numbers for my ellipse. Let me get rid of this because I'm going to need some room. So to get the third number, we're going to use our formula c squared equals a squared minus b squared for the ellipse. Switch the b and the c to get it back to its real form, because this is how we started ellipses. And then plug in what I know. So b squared is equal to 9/4 minus 1/4, better known as 8/4, better known as 2. So b squared is equal to 2. And I'm going to leave it like that because in the bottom of my formula is b squared. Okay, so the last thing I have to find is the center. So the center is the midpoint between x equals negative 2 and x equals 1, and midpoints are averages. So all we have to do is add them together, divide by 2. So negative 2 plus 1 is negative 1, divide by 2, and you get negative 1/2. So my final equation, I'll do it in green, and I'll write really finely, is going to be x minus a half, because it was the center is at negative 1/2, 0. Oops, that would make that plus, squared, over a squared, which is 9/4, plus, it's going to be y squared by itself because we move neither high nor low, that's a square, over b squared, which is 2, is equal to 1. So there's the equation of my ellipse, and now I can graph it, and it's not really that hard. All right, so let's finish this off. Here's our equation. We already know all our numbers. We know a is equal to 3 halves. We know b is equal to, in this case, the square root of 2 is, and, well, it will. C is equal to, and I forgot again, I think it's a half. There we go. All right, and we know the center point of this is negative 1/2, comma 0, center. And that's all we really need to know. All right, So let's put our center here. And this is why I wanted to scale my graph different than my pretty graphs. And let's plot what we know. All right, so if that's a half, then this must be 1. And I know my ellipse hits there. Oops, I'm going to have to draw my graph a little bit longer. And if that's a half, that's 1. 2 would be over here, so here's -2. And that's the width of my ellipse. Now square root of 2 is like 1.4, yeah. So if this is like a half, then 1.4 would be up here someplace. So there's 1 point on my graph, 1.4 up and 1.4 down. So this would be negative square root of 2. This up here would be positive square root of 2. And these are points on my ellipses. And I know one of my foci, and I'll do it in a different color. This is foci 1. And this distance is a half, so my other foci is going to happen at -1. And this is foci 2. And then my picture of my ellipse would go through these points. And that's the graph of the ellipse, which is the same thing as r equals 4/3 plus cosine of theta. So this picture is 4/3 plus cosine of theta. Not a perfect picture, but decent enough. All right, so an up-down conic, the picture changes a little bit. Now we have y is equal to d is our directrix, and then, things just turn from horizontal to vertical. So dp is now a vertical line segment. But theta is still here because we're still talking about polar coordinates, and we're opening up this fp, which is still going to be this length of r. And then the only thing we need to figure out to get everything right, because the same formula still applies, pf over pd is equal to our eccentricity, and therefore the magnitude of pf is equal to the eccentricity times the magnitude of PD. We could kind of think of them as vectors. And PF, of course, is equal to R, so I still need to find out what the heck the length of PD is. And, kind of like before, when looking at PD here, that this distance here is D, from y equals D down to the x-axis. So therefore, all I have to do is find the length from P to the x-axis and then subtract it away, kind of like before. And then what happens here is we're looking at this side now. This is y, if you want to think of it that way, this distance. And that would be a sine function because y is opposite of the theta and r being the hypotenuse. We'd get sine of theta is equal to y over r, and therefore this side is equal to r sine of theta. All right, and then this piece becomes d, the entire distance, minus that r sine theta. Okay, so then we can go back to my other color. This becomes d minus r sine of theta. All right, so if this is the case, then we're going to get, after we mess around a little bit, r is equal to ed over 1 plus r sine of theta. So that gives us our general form of a conic section that is either facing up and down, or elongated up and down, depending on if you're talking about parabolas, hyperbolas, or ellipses. So looking at the book, they kind of said, we leave it up to the reader to show what happens when you have a directrix that's either x equals a negative number or y equals a negative number. And I started playing around, and it wasn't as easy as they put forward. So it only becomes easy if you draw the right picture. So here's the right picture. The directrix is here at y equals negative d, so I'm not making this go left and right. This one's going to go up and down. And, of course, we still have theta and we still have r as our radius of our populating of these points P. All right, so with theta and r, we're going to graph this function dependent on the distance between the foci and the directrix. All right, so this side is probably the easier one here to figure out. This side is the y-coordinate of this triangle. So this would be sine of theta is equal to y over r. So this side becomes r sine of theta. And this distance here is d, but y is equal to negative t. So for our definition of pf over pd is equal to our eccentricity, I already have pf is equal to r, so then the length of pd is of importance, and d is way down here. So the distance of pd is going to be the sum of these line segments. So the distance down is d, and the distance up is r sine of theta. So unlike when it's in the opposite side, when y is equal to positive d, with y equal to negative d, we're going to add the pieces together. So this is going to become r is equal to e times d plus r sine theta. And then that leads us to r plus er sine theta. Ooh, not plus. That was the whole point of this thing. This becomes minus er sine theta is equal to ed. And then that leads us to r is equal to ed over 1 minus e sine theta. So when we have a minus sign in the bottom, that means that the d is opposite sign. So that means y, in this case, is equal to negative d. The sign tells me that this is equal to y. So if this is cosine, then it would be y, x is equal to negative d. So sine of theta forces a y. Cosine of theta forces our directrix to have an x. Directrix. All right. So there's clues when you look at these equations of how to deal with them. So let's look at coming up with a graph of something of this form. So for example, let r equal 5 over 4 minus 4 sine of theta. All right. So the clues that we're looking for, number one, this is a minus sign, so we know it's going to be either x equals a negative number or y equals negative number for the directrix. Because this is sine, that tells me that y is going to be a negative directrix, along with this guy here. So those two pieces, just looking at this, I know that y is going to equal some negative number. All right, the next step is to get this 4 to become a 1. So this becomes r equals 5/4, 1 minus sine of theta. And that tells me right off the bat that the eccentricity is equal to 1 because the coefficient of sine is 1. So that means we're dealing with a parabola. Parabola. And the d, y equals negative d, where d is equal to, kind of equal to that number, but it's really easy with e equal to 1. So the top number is ed, so ed is equal to 5/4, but e is equal to 1, so d is equal to 5/4. Now be careful here. This is just saying that your directrix has a value of 5/4. The equation of your directrix is going to be from up here. So it's y equals negative d, which is equal to negative 5/4. So we're going to get a line down here at y equals negative 5/4. Okay, and I know my focus is at the origin. That's just general for these conic sections. All right, so let's go for the angles. Let's let theta equal to 0. If theta is equal to 0, the sine of 0 is 0, and you get 5/4. So you get r is equal to 5/4. So when theta is equal to 0, it's pointing in that direction. So in that direction, I'm going to have a point at x equals 5/4. All right. When theta is equal to pi over 2, the sine of pi over 2 is 1. Remember, we're going back to this equation up here. The sine of pi over 2 is 1, so you get 4 minus 4 on the bottom, which gives you an undefined point, so we're not getting anything out of this guy. Nothing. So there are no points facing up, which makes sense because a parabola opens up and only has one y-intercept, and in this case, it's not above the foci. If theta is equal to pi, then the sine of pi is also 0, and you also get 4/5, but it's 4/5 in that direction because pi points in that direction. So I'm going to get another point over here at negative 5/4 on the x-axis. So these are x-coordinates that I'm plotting here. All right. So r is still equal to 5/4, but that is not a positive x value because pi is pointing to the left. So theta is equal to 3 pi over 2. When theta is equal to 3 pi over 2, then sine of 3 pi over 2 is negative 1, and that becomes 5/8. So r is equal to 5/8. So we're going to get this point here at y equals negative 5/8. So I'm going to be really explicit with that one. That is 0, negative 5/8. This is negative 5/40, and this one is 5/40. Now, given those 3 points, I can draw the parabola. So the parabola looks something like this. But I also want to come up with the rectangular form of this parabola. So it's not that hard. It's actually kind of easy. I know what a is equal to. A is this value here, the distance between the foci and... I could have found this so much easier. It's the distance between the foci and the vertex. It's also the midpoint between the foci and the directrix. So once I had the directrix, I should have been able to find a. All right, so a is equal to negative 5/8. I want to make sure it's facing the right direction. And I know my general equation is going to be 4a, it's facing upwards, so it's going to be y minus something equal to x squared. The x-coordinate's not changing, so it's not going to be x minus something. So the y-coordinate was negative 5/8, so this becomes plus 5/8. And a is equal to negative 5/8, so that becomes 4 times negative 5/8. Y plus 5/8 is equal to x squared. And then that becomes negative 20, negative 10. Hold on. No, darn it. Negative 5 halves of y plus 5/8 equals x squared. Just in case you wanted to change it into a rectangular coordinate system. All right, this is my very last example. So we have here r equals 3 over 2 minus 5 cosine of theta, and we need to convert it. So we're going to convert it the same way. We're going to divide everything by 2 to start with. So we're going to get r equals 3 halves, 1 minus 5 halves cosine of theta. All right. Because this is the coefficient of the cosine, it tells us that the eccentricity is equal to 5 halves, which is bigger than 1, which makes this a hyperbola. Hyperbola. If E is equal to 5 halves as the eccentricity, then the top number is ED is equal to 3 halves. And if E is 5 halves, then we get this equation. It's not as easy as some of the other ones. We're going to multiply both sides by the reciprocal of 5 halves. So we're going to multiply both sides by 2/5. The 2's over here are going to cancel. That's rather nice. And then we're going to get d is equal to 3/5. All right, so we have the directrix and we have the eccentricity. All right, now we have to kind of analyze the beginning function. I forgot to do that at the beginning. So first off, this is a minus sign. So that kind of gives us an indication that it's not going to be d equals a positive number, or I'm sorry, x or y equal a positive number, or x or y is a negative number. So here, because it's minus, we know that x and y is going to be a negative number. Being cosine, it's going to be a negative x value. So this d translates into the directrix x equals negative 3/5. So that becomes part of our physical graph. So for all of these polar forms of conic sections, the focus lands there at the origin. Now this is going to be focus 1. The hyperbola has another focus someplace. X equals negative 3/5 is the directrix, so that's going to come over here. Hopefully I've given myself enough space. And that means when we're talking about this hyperbola, it's going to open up left and right somehow. All right. Then we still need to find a few other things. So let's let theta equal a few things in my original equation to find out some coordinates. All right, so let theta equal 0. That's a nice one to start with. And then r is going to equal, let's see here, cosine of theta is, cosine of 0 is 1. We're going to get negative 3 in the bottom. So this is going to give me r equals negative 1. So when the angle is pointing in that direction, my radius is negative 1, which puts my point beyond negative 3/5. So this would be negative 1. So that's one of my vertices. All right, theta equal to pi over 2. Cosine of pi over 2 is 0, so we're going to get 3/2. I'm not sure if that helps us any, but 3/2 would be something like up here. And theta being pi over 2, it would be pointing straight up, so we know it's going in the right direction. Give it that arrow. All right, and then theta equal to pi. Cosine of pi is also, well, not also 1. It's going to be negative 1. So that's going to give me 3/7. So r will equal 3/7, which is a little bit off this focus. Remember, our angle's pointing in this direction. It's pi. So 3/7 is going to be here at negative 3/7 on the x-axis. Okay. And then theta equal to 3 pi over 2. Cosine again is equal to 0. And we get our 3/2 again. But the problem now is it's not going up, it's going down. So we get 3/2 down here. 3/2. And this would be negative 3/2 on the y-axis. And then, of course, theta equals 2 pi. And we're back to cosine equaling 1. And we're back to r equals negative 1. So it kind of just generates that same point again. All right, so that gives us a few points. This point is of interest. That is a vertice of my hyperbola. And it has a specific distance away from my foci, which is kind of nice also. So my other foci must be 3/7 away from negative 1. So I need to move the correct direction. Notice the foci here is to the right of that point, so I need to move to the left 3/7 units. So I'm going to subtract 3/7 from 1. So let's see, negative 1 minus 3/7, that's negative 10/7. So we're going to have this coordinate over here, which is negative 10/7, and that actually is the second foci. So here's my first foci. I'll change the color of it. And there's my second foci. Now remember, those aren't part of the graph at all. And later, I'm going to use my 3/2 and negative 3/2 to help me graph this function. All right, so number 1, let's look at this. This is called the major axis. And again, that's equal to 2a. So if that's 2a, then we can say that the distance between -1 and -3/7. So to do distance, you are going to subtract the numbers. Absolutely. Oops. Absolutely. And that's going to equal 2a. So that becomes -1 plus 3/7, which would be 4/7, is equal to 2a. And therefore a is equal to 2/7. All right. So that gives me what a is equal to. And to find c, I can use the formula, the eccentricity is equal to c over a. I know my eccentricity is way back over here, is 5/2. I know a is equal to 2/7, and therefore c is going to equal 5/7. Okay. And then that just leaves me to find b. So b is for the formula of a hyperbola. I know this is a hyperbola because the eccentricity is bigger than 1. I don't know why that stray mark is there. Left-handedness. So to find b, we're going to use the formula c squared equals a squared plus b squared. And then therefore this is going to be c squared minus a squared is equal to b squared. And that implies that we're going to get 25/49 minus 4/49 square rooted is equal to b. So let's see, that's 21/49, so we're square root of 21 over, so as a decimal, let's see here, that would be square root of 21 divided by 7. About 0.65. Approximately, let's get this out of the way, approximately 0.65. Yeah, give or take a little bit. All right, so b is equal to 0.65, and that means from the vertex, we're going to go up 0.65, which is, if this is 1, 0.65 would be right about there. And we're going to create our rectangle, go down 0.65 and right 0.65, and we're going to do our little diagonals through those points. Oh, that's a horrible one. So I kind of gave up trying to draw this by hand. It wasn't working out with my unlabeled axes as well as I wanted it to. So I did this on a computer to make sure that the picture came out perfect. So I drew in here the rectangle where this is 0.65 distance off the vertex, and then of course the a distance, 2a distance across, and the same thing up and down. So I drew my rectangle in. I still have my -1.5 and my 1.5 points in there. And that's what I wanted them for, is to be able to pass my hyperbola through them so that I could draw this part of the graph along the asymptotes. And then the other one, we would have just had a guess at where it was going. I found the vertice there of -1, and then this would be our hyperbola. So it's kind of a cool idea, this conic sections as polar equations.